Hello. In our series on kinetic theory of gases, having discussed about the degrees of freedom as well as the law of equipartition of energy, we are now discussing the relation between the ratio of the specific heat capacities, which is usually indicated as gamma, and the degree of freedom that we have denoted as N. Now, as far as the equipartition of energy is concerned, we had obtained the expression for the internal energy of a system of gases, and that being equal to N over 2 times of RT, where N is again the degree of freedom. And as far as the specific heat with a constant volume is concerned, we have it as CV, which is the specific heat capacity at constant volume, and that is simply the rate of change of internal energy with respect to the absolute temperature. And with that being applied to the expression for the internal energy on the left, we get that to be equal to, that just gives us N over 2 times of R, with the T getting cancelled out, or the derivative of T giving 1. And as we know from Mayer's formula that Cp minus Cv is going to be R, that is the universal gas constant. So here we have Cp to be equal to simply Cv plus R, and Cv, as we know, is N over 2 times of R. That added to R is going to give us N plus 2 over 2. So that's the value of Cp. We have the value of Cv. The R stays there as well. So with those values now available to us, we can calculate the value of gamma, that is the ratio of the specific heats that we denote with gamma, as I said, which is a Cp over Cv, and Cp over Cv is just going to give me the 2's and the R's get cancelled out. We have N plus 2 over N, and that is simply, that can be written as 1 plus 2 over N. Now, as for the monoatomic gas, we have the monoatomic gas, and for that we have N is equal to 3 as discussed earlier. So we have the value of gamma. For in that case, the general value that we have is 1 plus 0.67 is 2 over 3 is 0.67 for N is equal to 3. So we have that value to be is equal to 1.67. So will be the case with diatomic gas at very low temperatures, which is less than 250 Kelvin. But for diatomics at medium temperature, we already know the value of N in that case is simply equal to 5, and using that in the above formula over here, 1 plus 2 over 5 is going to give us 1.4, because 2 over 5 is 0.4, so 1 plus 0.4 is going to give us 1.4. Now, the case of diatomic gases have at very high temperatures, which is usually above 750 Kelvin, and for that, although we get N is equal to 6, but for calculation purposes we know that we are taking it to be 7, and so 1 plus 2 over 7, 2 over 7 is going to give us 0.29, and 1 plus 0.29 is 1.29 approximately. So these are the values of gamma for different gases and the different types of gases, and with the degrees of freedom being different, we have the value of the ratio of the specific heat capacities to be different as well. So this is how we will be applying them. These are the values that we'll be applying them, will be applying for calculation purposes in different numerical based numerical value problems. Now we have the next segment as the mean free path. We already have discussed about the mean free path in our prior to the postulates drawn for the kinetic theory. Here we'll be trying to obtain an expression for the mean free path, and as we know that it is the The free path is the straight line between the two successive collisions that a gas molecule experiences. So if this is the first one, this is the second one, and this is the third one, the first one strikes the second one, and it collides with it and gets supposedly deflected towards the third one. Now, as it moves from the second to the third after the first collision, that is with the second, then it will take a straight line path, and that is the mean path. And with multiple number of such collisions, we can take an average of all such collisions, and we have the path, that is the free path of all the molecules concerned. Then we obtain the mean free path. Now, in order to obtain a mathematical expression, we draw some assumptions so that we can obtain them easily. Now, the first assumption is that while the molecule that is under observation is the only one that is moving, so molecule under observation is in motion while the others are at rest. This may look a bit absurd, but still we can, for calculation purposes, consider it. Then we'll see if we come up with some correction. In fact, Maxwell came up with a correction related to this, and we'll be introducing that later in the video. Now, secondly, what we consider is that the molecule is to be considered as a sphere of a certain diameter. Let the diameter in this observation, or in this expression that we are about to obtain, let the diameter of the molecule be taken as d. So the molecular diameter in this case is d. We're not concerned about the radius over here, because we'll be getting the expression in the form of the diameter, so we are taking the diameter as a whole. Now, the two molecules are said to have collided with each other if their centers are separated by a distance equal to or less than d, which is fair enough, because if we are considering two molecules, so this is one molecule and this is another molecule which must have collided. Of course, they are touching each other. There may be some compression between them, which will lead the diameter being d, the distance between the centers of the molecule must be d, or probably less than d as well. That we can afford, because this is an elastic collision that we are considering in kinetic theory. So it should be d, or even less than d, a bit less than d, not exactly very less than d. So that is these are the assumptions that we take into consideration, and we obtain the expression as follows. Okay, so we have to consider this figure over here in order to obtain that expression. Now, we are considering a molecule which is there at the center, shaded, which I'm showing with a dot at the center. And that molecule is supposedly, that's not outside, that's actually the patch that we have shaded in that cylindrical region. So the molecule is in that cylindrical region that we have shaded, as you can see. Now, that molecule travels with a with a speed v, with a speed c, supposedly c, not necessarily the velocity of light, but the root mean square speed that we have been usually denoting with the letter c. So as it moves forward, it can be said to have collided with all the molecules that is contained in that cylinder of a certain radius. Now, the radius of the cylinder, let us say let us take the radius as d, because d is the diameter of that of the molecule that we are considering, and also d is the radius of the cylinder that we have taken. So what it does is that it leaves no other space for the molecule except for that axial line along which it can pass, that is along the axis that we have AB. We have denoted that axis as AB. So that is the path that is left for the molecule to move, because at the top, as you can see with the dotted or dashed lines that I have drawn, the two molecules at the top and the bottom. So at constant collision with molecules at top and bottom, the path that is left for the given molecule shaded is to travel along that straight line along the axis along AB direction, and it travels with a speed c, of course. Now therefore the collisions with the collisions with this molecule is not possible, that is outside the region D or outside the distance D. And with that cylindrical region in consideration, we are taking the cylindrical region PQRS. That is the volume through which it is moving. That is the volume of the cylinder that we have considered, and the volume over here we can express it as volume to be equal to pi, radius being d, pi d square, times of the distance. Now the distance that it will take is equal to, in 1 second, because c is its speed, so this is the volume that it travels in unit time. So volume of the cylinder that has been in unit time we are considering the volume, and that volume is obviously equal to the length, that is equal to the speed of the given molecule. Now the number of molecules that will be contained within that given volume will be equal to n times of it if n is the number of molecules per unit volume. If n is the number of molecules per unit volume, then we have the total number of molecules in the volume to be equal to n times of that, so n pi d squared c. So that gives us the total number of molecules that are contained within that cylindrical volume. Now the number of molecules or the number of collisions that will be taking place in 1 second will be equal to the number of molecules, which is also equal to the number of collisions possible. Per unit time, that is in 1 second that we are considering. Now with that many number of collisions, if del t is the time taken or the time period of collision, then the interval between two successive collisions on an average will be equal to 1 over the frequency of collisions. So that will be equal to the total number of collisions that is taking place in 1 second. So that is equal to 1 over n pi d square c. Now with that being the time taken, so the mean free path is just going to be, the mean free path is usually denoted by lambda. So the mean free path can therefore be expressed as lambda to be equal to the speed times the time period. Now the time period for the collisions, that is. And so in this case the c gets multiplied to 1 over n pi d square c, and the c's get cancelled out, and so what we are left with is simply 1 over n pi d square. This is the expression for the mean free path. Now as I mentioned that this assumption that we have taken, that the molecule under observation is in motion while the others must be at rest, well, that was put to rest, that assumption was put to rest by Maxwell on the basis of his velocity distribution results, and the correct value that was therefore obtained, I am writing it over there in that term, so the corrected value that was obtained was equal to 1 over root 2 times of the expression obtained. So corrected value for lambda is 1 over root 2 times of pi d square n. So this is the expression for the final expression for the mean free path. Also, what we come across is that this N that we have obtained over there, as we know that for pressure P, that is the gas may be having, P is equal to nkt, and so we have N to be equal to P over kt, and this P over kt can be put there instead of N, and we have the expression for the mean free path to be equal to the N term is P over kt, so P stays down and kt goes up, so kt over root 2 pi d square, and P over there at the denominator. So what we get is that this mean free path, that is directly proportional to the absolute temperature, that is inversely proportional to the square of the diameter of the given molecule, and also that is inversely proportional to the pressure of the gas. So these are the observations that were obtained, uh, and also the case that it is inversely proportional to the number of molecules per unit volume, because firstly we had obtained the expression where N was in the denominator, so uh, we have that to be inversely proportional to N as well. So actually the pressure term need not be considered because we have N. So either case we can take this or this. Probably we can take the number of molecules per unit volume in that case. So that's more or less the expression for the mean free path, and then in the next upcoming videos we shall be discussing few numerical problems as well as the other concepts that are associated with this topic. Till then, thank you for watching.